My name is Ayush, and welcome to my talk on implementing ingestion and enrichment pipeline for Beam. A little background about me. I was a grad student at University of Colorado, Boulder. I pursued masters in data science. So I was also fortunate enough to be selected for Google Summer of Code Fellowship twice. Last summer, I worked on Apache Cloud Stack, which is an infrastructure as a service cloud orchestration tool, where I directly worked with different hypervisors such as VMware and KVM at a very low level. This summer, I worked on Apache Beam for implementing the RAG pipeline to be able to add to the semantic search pipeline use case in Beam. Currently, I'm working as a machine learning engineer at MicroStrategy. So the first question is, what is RAG? Since there have already been two talks about RAG, I know a lot of people would already be knowing what RAG is, but I would still give a little introduction of RAG just in case if someone just joined. RAG stands for Retrieval Augmented Generation. It's an AI framework which is used to generate accurate and relevant text using large language model and traditional content context retrieval system. So in RAG, the retrieval stands for retrieving the relevant chunks for from the knowledge base using semantic search. So semantic search could be a lot of things, such as one example would be based on the similarity search. I would not go too much in detail about it. So the second is augment. So augment is basically augmenting the user prompt with the relevant information that we have fetched from the knowledge base to enhance the context. And then comes the generation where we provide this enhanced context to the LLM to so that the LLM can generate more accurate and usable prompt. So now the question comes is like, why RAG? Why do we even need to use RAG, and why it has become so popular? So there are few limitations with the traditional large language model, such as they are not able to produce the relevant text because they are trained on general text corpora, which makes it really hard for them to produce the relevant text. So they tend to hallucinate. So that was one of the major reasons why RAG came into picture to use the hallucination that a lot of large language model do. So the other problem with LLMs is that they are foundationally trained offline. So it becomes really hard for us to incorporate the new data and to be able for us that the LLM is able to ingest the new data, we have to like retrain or fine tune the model, which again is a very expensive job. It is time consuming and it requires a lot of resource. So now let's talk about why it is so popular. So with RAG, we don't really have to, first of all, it is model agnostic. We can try different models and we don't, it's like we have a separate knowledge base. It could be a database where we can keep the updated data that we want the LLM to predict. It can have some domain specific information, or it can even contain some proprietary information of a company. So in case of RAG, we just have to like fetch the data from the database, which is way more efficient and less time consuming when we compare it to fine tuning a model. So let's quickly look into the RAG architecture. So this is a high level overview of how the RAG architecture looks like. When the user gives a prompt or a query, then we fetch the relevant information from the knowledge source. And once we have the relevant chunks information, we would augment it into the user prompt to enhance the context. And then we provide this enhanced context to the large language model so that they can predict or they can generate the answer better. Now, how we can use Beam to implement the RAG pipeline. So for implementing the RAG pipeline, I use foundational Beam modules such as ML transform and enrichment. So I had to write the custom IO class for different vector databases that I use. So I used two vector database. One was Redis vector database. The other one was OpenSearch. So first of all, I implemented different chunking strategy using line chain libraries such as split by token, split by character, recursive split by character. Then I use Beam's ML transform module to transform the data and use sentence transform embedding to generate the embeddings. Then we use enrichment source handler for searching the relevant chunk in the vector database. So this is how RAG ingestion pipeline looks like. We are first of all ingesting the document, then we are dividing the document into small chunks for better context. So here we can see there are two write queries. One is directly we are storing the chunks directly into the vector database or our knowledge base. The other is we are generating the embeddings for these chunks, and then we are shooting the update query to save these embedding along with the text or the chunks that we have saved in the database. If we talk about the Beam equivalency, so first we have the document, and then we can use a very simple root p transform. It could be like beam.create to beam.create, which is nothing but a list of dictionary. It could be like retrieving our data from the cloud sources such as AWS, GCP, and then I'm using the transform to transform the document into different chunks. So the second P transform is a platform aware transform, which is like where we are like setting up or connecting to the vector database, and then we are writing the chunks into the ISM. So when I say platform aware transform, it means that the code will be different for different databases. Like it will be different for Redis vector database, and then it will also be different for OpenSearch vector database. Then the third transform, P transform, is where we are converting the P collection text into P collection embedding. And then the fourth is again a platform aware transform where we are ingesting the embeddings into the database. So here, like I mentioned before, we have two insert queries. One is the insert query, the other is the update query. So this is how my ingestion pipeline looks like. As well as we can see using the sentence transform embeddings, I've passed a model name. I have also passed the columns for which I want to generate the embedding. In my case, my columns look like the URL, the text, the title. So in this case, I generated the embedding for text and title. And then I use chunks generation, P-transform, to chunk is based on different chunking strategy, like split by token, split by character, or recursive split by character. Then we are ingesting the chunks into our Redis or OpenSearch vector database. And then we are using ML transform to transform our database. And the other update query is using insert embedding in Redis, where we are basically updating our database and adding more columns as in text vector or title vector, which contains the embedding for the text and the titles. The reason I did it because the way ML transform has been implemented is that it will transform data from one form to another form. So in this case, when I was ingesting the text data, it was just providing me the embeddings. It was replacing the text data. So I wanted the text as well as embedding. So I had to write two write queries. So this is how my chunk generation P-transform looks like. I'm not sure if it is very visible, but this is most of the code that I could get into one snap, and it is still not complete. So if you see here, we are taking the chunking strategy from the user. we are taking the chunk size as the input, the chunk overlap as the input, and then we are calling the pardo function. Inside this, the logic is written. So now talk about the enrichment pipeline. This is how the RAG enrichment pipeline looks like. We get the query, the prompt from the user, then we are generating the embeddings for this query or prompt, and then using the semantic search such as cosine similarity in the vector database, we would find the relevant chunks, and I'm just spitting out or yielding the relevant chunks along with its embedding. So if we compare it with the Beam equivalent pipeline, so the first transform again would be a root transform as beam.create, where the input or the prompt that has been given by the user, we are transforming it into the P collection. Now, this P collection again is transformed into embedding P collection, text P collection, and then the P transform 3 is basically an enrichment handler, which behind the curtain is again a P transform, where we are just enriching, which we are using to get the enriched result. So, like I told in the last slide, for the P transform one, we are just transforming the data to P collection using the root P transform. For P transform two, we are transforming from Gaussian P collection to embedding P collection using the ML transform as before. And the third P transform three, or enrichment, where we are loading the additional context from vector database to enrich user's question before augmenting the user prompt. So this is how my enrichment pipeline looks like. So here, the data is how the input looks like. The text would be the name of the column, and then like what is in our case is the value. And then we are using sentence transformer embedding to generate the embedding for this prompt. So once we have the embedding, we would be passing it to the enrichment class. So the Redis enrichment handler is basically inheriting the source enrichment handler, which is basically a wrapper, and we just have to override the call method, and we have to just write the implementation. Again, it is platform dependent, so the code is going to be different for different vector database which we are using. So this is how my Redis enrichment handler looks like. As you can see, the enrichment source handler, it takes beam.row as an input and it yields or emit beam.row as an output. Here we are taking the Redis host, the Redis port from the user input. So user can also provide the index name, the vector field, and the return field which user wants to emit, or by default, I have declared it. And K stands for the nearest neighbor that we want when we are like running the search query. So based on the K nearest neighbor, it's going to give the document or relevant chunks. So inside the call function, first of all, we are generating the embeddings of the input or prompt given by user. So here I have used vector field dot strip underscore vector, because the way I am storing data in the vector field as a different column. So the text contain the text data, the title contain the title, which is again a text, and then we have a text vector, which is the embedding of the text column, and then I also have a title vector, which is the title embedding of the column. So if the user gives the input in the form of text, as in the key is text, then we can just get the embedding for text vector. If user names it as a prompt or a question, so we are just going to strip the before part and we will just focus on the vector and we'll get the embeddings of the given input. So this is the base query or the search query like that I wrote, and then we are performing the vector search and we are emitting the beam.row. So we can see I'm emitting the embedded query as well as relevant documentation, the docs which contains the relevant data. So I'll quickly talk about the inference pipeline. This is something that I haven't implemented till now, but I am planning on working towards it. This is more of a future scope thing. So once the inference pipeline is implemented, this is how the overall flow would look like. Once we have the relevant data from the vector database, we can just augment this relevant data with the user query on input, and then we will provide it to the element. And based on the text or data that is generated, we will pass it back to the user. So to conclude, as we can already see that RAG is like fairly simple, and it's a streamlined process, and it can be implemented with Beam's existing tools at scale for rapid prototyping and deployment. So there are a few gaps I observed. The first one, I would not really say it's a gap, just that it did not really fit my use case, because the ML transform which has been implemented is in a way that it will transform the data from one P collection to another. So this means for my use case, I have to execute one insert and one update query instead of just one insert query where I can insert the text as well as embedding. The gap I observed is that there are very less native Python support for vector database queries meant for writing the custom IO class or Python client. So I had to write the custom IO for Redis and OpenSearch vector database. So the next step would be I would want to integrate these custom IO connectors that I wrote for my project into the Beam Foundation package so that it can be used for reusability. And someone who is making building a RAG application and they want to use the Redis or OpenSearch database, they can directly use it. And the other one would be expanding the RAG pipeline to augmented generation, which we can implement using the Beam's inference API. So last but not the least, I would want to give a big shout out to my mentor, Danny and Jack, for their immense support and guidance throughout my GSOC fellowship.